We're continuing with Chapter 5 in the statistics textbook. In this video, we're going to go through section 5.3, which is on the normal approximation for data. So in section 1, we were introduced to the normal curve. Then in section 2, we strictly looked at how we can find areas under the normal curve over any interval we want. And now in section 3, we're going to bring all of this together. And so as we've gone through section 1 and 2, I've talked about the purpose of what we're learning the normal curve for and what we're finding areas under the normal curve for, which was just so you're making an assumption that some statistic amongst a population, like all people in the United States, for example, you're making an assumption that that data, that statistic is normally distributed. So for example, all of the heights of everyone in the United States, 18 and older, let's say. We don't know that exact histogram. I don't think you could easily get that for everyone in the United States. But if you could assume that that histogram would be distributed normally or close to normally, then with that you could estimate, okay, well, how many people, what percentage of all of the data points of everyone in the United States 18 and older has a height between this height and this height? And you would use the area under the normal curve along that corresponding interval to get that estimation. It would be an estimation, but it would be potentially a good estimation, assuming your assumption that that data is normally distributed is a good assumption. And so I mentioned what the purpose of what we were learning was as we were going through sections 1 and 2, but we're gonna go through that more officially here in section 3. Now, one thing I do want to point out before we get started is, so you might be asking yourself questions like, all right, what we're going to do, the examples we're going to do in this section are going to be based on heights in the Haynes 5 study, heights of men. And we did, in the previous couple of videos, we looked at examples for heights of women in the Haynes 5 study. Here was that histogram in the background behind the normal curve. Okay, but so first of all, I've been mentioning that, if we have the actual histogram for what we're trying to analyze, then we don't need to use the normal approximation. Just go to the actual histogram and calculate the exact area. Yeah, absolutely. But then I mentioned that you can think of it like, if you take if you're trying to understand how something is distributed throughout everyone in the United States, and so you take you do a sample of 100,000 people, let's say, and get their heights. And if that data is distributed close to normally, then maybe you could assume that that same statistic for everyone in the United States is normally distributed. So you would use the normal approximation in that way. But then you might ask, well, that's fine, but how do you know what the average is? How do you know what the average of that statistic is for everyone in the United States, or the standard deviation? Well, first of all, you could potentially assume that the average and the standard deviation are the same as the 100,000 people. That's kind of, you call it the sample average and standard deviation. But these are topics that we're going to learn as we go through this course, as we go through this textbook. And so what I want to state here is, don't get bogged down with these practical questions right now. We're going to explain all this stuff. I'll explain all this stuff as we go through the course. And when it comes time, I'll come back to topics like this and explain them, how they applied. Because again, what we're doing is we're about to, we did examples where we're doing a normal approximation for this histogram here. This was for women, but we're in this video we're going to do examples for men. But why are we even doing this? We've got the actual histogram. We can see the histogram in the background. Absolutely. So if we have the actual histogram, then you don't need an approximation. Just use the histogram, of course. But this is just so we can learn the concepts. It's too advanced to talk about at this moment concepts that would relate to, okay, we're a real situation where we don't have the histogram and we need to use the normal approximation. So we're going to use the normal approximation, but what are we going to assume for that normal curve? What are we going to assume for is the average and standard deviation, right? Because we need to convert to standard units. To convert to standard units, we need to assume an average and assume a standard deviation for a histogram that we don't know what it is. That's why we're using the normal curve assumption, right? So what do we assume for the average and the standard deviation? Don't worry about all that right now. All we're doing is we've got a histogram. We're just learning the normal curve idea. We've got a histogram, okay? And we're going to assume that data itself, we're not saying that we don't have a histogram for a sample of something, and then we're going to assume that the population is normally distributed, right? Like for students at a university, we took data for a sample of students, and now we're going to make an assumption about the entire student body. No, we've got some data, okay? We've got some data. All we're doing right now, it might seem non-intuitive, is we've got some data, okay? We can calculate the average and the standard deviation of that data, and then instead of drawing the histogram, which, I mean, to me, if you could calculate the exact average and the exact standard deviation, why couldn't you've got the data points, so make the histogram. But with that exact same data, we're not assuming like we're thinking about a population. With that exact same data, we're assuming it's normally distributed with a normal curve. I know it doesn't make sense. This is just how we have to start at the beginning of the book to learn the concepts. You get what I'm saying? If you calculated the standard deviation and the average with those data points, then you have to have the data points. So why don't you just make the histogram and calculate the areas under the actual histogram? Sure, that's what you would actually do in practice. Okay, but we're just trying to learn here. We've got the data, we have the average, we have the standard deviation of that data, and instead of drawing the histogram, we're assuming that the data is distributed with the normal curve. So we're using an approximation, and we're going to calculate areas under that normal curve to approximate how many data points are within certain intervals of the actual histogram, which we then actually do have, and we can we have the actual histogram, and we compare what the actual percentage is to the assumption. But again, it's not intuitive. It's like, why would we ever do this? You would never do this in practice. In practice, you don't have the actual histogram. But again, it's too advanced right now to explain, to look at it like like we would in actual practice right now. We can't talk about it like that yet. All right, so with that in mind, let's take a look at section 3 here. So the method for the normal approximation will be explained here by example. All right, the heights of the men age 18 and over in Haynes 5 averaged 65 inches, and the standard deviation was 3 inches. Use the normal curve to estimate the percentage of these men with heights between 63 inches and 72 inches. Okay, so of these data points, we're not talking about all of men in the United States at this time. All we're talking about is just the data points in the Haynes 5 study, all of the men that were involved in the Haynes 5 study, age 18 and over. Those men literally averaged 69 inches, and the standard deviation was 3 inches. And again, if you could calculate the exact average and standard deviation, that means you have the data points. So why not just make a histogram out of those data points and calculate the exact percentage between 63 and 72? Of course, that's exactly what you would do in real life. But just for practice, let's assume that we don't know the histogram, but we do know the actual exact average and standard deviation. You can imagine when we get to later chapters, we're going to have to make an assumption about the average and standard deviation as well. But in this circumstance, we know the exact average and standard deviation, and we're going to assume that the histogram is distributed with a normal curve. Now with that, and we don't know the histogram, so with that, let's estimate the percentage of these men in this exact study that had heights between 63 and 72 inches. So how do we do that? With everything we learned in section 1 and 2, how can we answer this question? Well, all right, so remember what we talked about in the previous videos. We've got this original histogram, something like, okay, and so each of the bin endpoints was like, 57, this was 59, 61, 63, 65, right? Each of the inch values lined up with the bin endpoint. You don't have to have equal bin widths, but I'm just drawing it that way here. But the first idea was you need to convert to standard units. And there was 2 ways we looked at how you could think about doing that. What you could do was you could just erase the original horizontal axis and at the average put 0, and then go plus or minus 1 standard deviation. You just put the markers. But the thing is, the markers aren't going to necessarily line up with any bin endpoints. They're just going to be at some arbitrary position, like in the middle of, or at some arbitrary position within a bin, right? These don't line up with the endpoints. You could do it that way, or you could, and what we did with the batting average histogram, we converted all the values to standard units, and then just made a new histogram with the standard units. And so that way the bin endpoints actually did line up in a certain way. Like, the bin endpoints were where the markers were. That's how you convert to standard units, but it doesn't matter. You can do it either way, because once you convert to standard units, what we're doing is we're in standard units and we're assuming that our histogram follows a normal curve. We're assuming that if we convert our histogram to standard units, it follows the normal curve. The normal curve is in standard units. It has an average of 0 and a standard deviation of 1. That's the assumption. I'm going to say this again. We have a histogram that we know its exact average. We know its exact standard deviation, but I guess we kind of don't know its shape, you could say. But we're assuming that we can make an assumption that if we did convert that histogram to standard units, then it would closely line up with the normal curve. Where in standard units, it's that normal curve is centered at, its average is, it's symmetric, its average is 0, and its standard deviation is 1. If we were dealing with another kind of histogram that was skewed or something, then we haven't talked about that yet. We're not talking about a skewed histogram. We're not talking about a histogram that isn't symmetric, that you can't assume is symmetric, at least. We're not talking about that. Okay, so if we quote unquote don't know the actual distribution, but we know the exact, for some reason we know the exact average and the exact standard deviation, we're assuming that when converted to standard units, I just talked about how you convert to standard units. When converted to standard units, that distribution would follow the normal curve. Then what would approximate, if we don't know the actual distribution, then let's estimate the percentage of these men that had heights between 63 and 72 inches. How do we do that? Well, we're going to convert these to standard units. And then what? And then just calculate the area under the normal curve between whatever these standard units are. We just did that in the previous video. It's easy. Okay, so what is this in standard units? What is 63 and 72 in standard units? That's easy. We've done this countless times now over the last few videos. How far does 63 deviate from 69? Minus 6. What about 72? Plus 3. How many standard deviations is minus 6? Well, standard deviation is 3, so this is minus 2 standard deviations. How many standard deviations is 3? It's plus 1. So let me erase this. That's it. It's 63 is minus 2 in standard units. 72 is 1 in standard units. Okay, what's the area under the curve, the normal curve, between minus 2, the interval on the interval minus 2 and 1? That's what we did in the previous video. Okay, in the last 2 videos, I go into detail on exactly how we do this, but let's put this formula for the normal curve into our graphing calculator. Store it as equation E. Now we do a direct integral of equation E with respect to x from along the interval minus 2 to 1. 81.9. So the percentage of these men in this study with heights between 63 and 72, we can estimate with the normal curve that it's 81.9% of data points. There's 81.9% of the men in the study had a height within this range. There you go, 81.9, that's 82%. That's this area. Okay, so using the normal curve, we estimate that about 82% of the heights were between 63 inches and 72 inches. This is only an approximation, but it is pretty good. 81% of the men were in that range. Okay, so we have the actual histogram, and here's the actual histogram. Here's the normal curve, and the actual histogram, it was 81%. It was actually 81%, and we got 82%. So, it's a good approximation, right? But again, why wouldn't we just use the actual histogram? We would in practice. This is, and you can imagine in later chapters, we're not going to have the actual distribution. So we're going to talk about, well, how do you know how good your assumption is, right? If you assume that it's normally distributed, how good of an assumption is that? We can calculate things like that. But you're assuming what the average and the standard deviation are as well. How good of an assumption is that? We'll talk about all that. All right, the heights of the women age 18 and over in Haynes 5 averaged 63.5 inches. The standard deviation was 3 inches. Use the normal curve to estimate the percentage with heights above 59 inches. All right, so we're assuming that the women in this Haynes 5 study, that list of data points, not about the entire population of women in the United States, were just that literal, all the data points. I think it was 3,000 data points, women age 18 and over, their heights. It's like 3,000 data points. We know the exact average. We know the exact standard deviation. And we're assuming that it was distributed normally. So it was symmetric about the average and, had a shape like this, right? How can we estimate the percentage of women in this study that had heights above 59 inches? Well, what is 59 inches in standard units? How far is 59 from the average? It's minus 4.5. So minus 4 1/2 is equal to minus 9/2. Okay, how many standard deviations is that? Minus 9/2 divided by 3. So that's times 1/3 minus 3/2. Okay, so the question is, what's the area under the normal curve from minus 1.5 to infinity? That's the question, right? What's the area under the normal curve with above minus 1.5? How do you do that? We go from minus 1.5 to infinity. That easy. 93.3%. There you go, 93%. Using the normal curve, we estimate that 93% of the women were more than 59 inches in height. This estimate is about right. 96% of the women were taller than 59 inches in the actual histogram. So you see, it's a good estimate. It is a remarkable fact that many histograms follow the normal curve. The story continues in part 5. Okay, that's interesting, right? Many histograms follow this normal curve. Pretty closely, not exactly, but closely, like we've seen here. For such histograms, the average and standard deviation are good summary statistics. If a histogram follows the normal curve, it looks something like the sketch in figure 4. Okay, so yeah, like if you have a histogram that you can assume is normally distributed, it's like we've seen, like we saw with the heights, and they're just giving another example here, right? It kind of follows that normal curve, and it's saying it's remarkable how many histograms behave this way. They look like this. You can approximate them with a shape like this, right? So symmetrical about the average and then distributed in this way, right? You could be symmetrical about the average and not follow and be distributed differently than the normal curve. But there's a lot of, it's remarkable how many histograms are symmetrical about the average and then follow a shape like this. The average pins down the center and the standard deviation gives the spread. This is nearly all there is to say about the histogram if its shape is like the normal curve. So what are they saying here? So first of all, many histograms follow that normal shape, okay? And if that is the case, then the average and the standard deviation are great summary statistics for that data. You can use the average and the standard deviation and that will give you that will tell you, they're saying here, pretty much everything you need to know about that data, okay? But look here. Many other histograms, however, do not follow the normal curve, which makes sense. In such cases, the average and the standard deviation are poor summary statistics. Interesting, right? So if you have a distribution, a set of data, a list of data points, that it doesn't follow a normal distribution, which many do, then you can still calculate the average and the standard deviation. You can do that with any list of numbers, but those aren't the best descriptive statistics to use, or they're poor, actually, for that type of data. The average and the standard deviation are great for data that's normally distributed, for a list of numbers that's normally distributed, but it's a poor descriptive statistic for data that isn't distributed normally. And so how do you describe that kind of data? We're going to talk about this in the next section. Okay, let's go ahead and work the example problems for this section here in this video. For the women age 18 to 24 in Haynes 2, the average height was about 64.3 inches. The standard deviation was about 2.6 inches. Using the normal curve, estimate the percentage of women with heights below 66 inches, between 60 and 66 inches, above 72. Easy. Convert these to standard units. How far is 66 from the average 64.3? Positive 1.7. How many standard deviations is positive 1.7? 0.654. All right, let's convert 60 and 66 to standard units. How far is 60 from 64.3? It's minus 4.3. How many standard deviations is minus 4.3? Minus 1.65. Okay, 66. How far is 66 from 64.3? 1.7. We just did this. So this is positive. Oh, yeah, we just did this. 0.654. Okay, what about 72? 72 is 7.7 above 64.3. And how many standard deviations is that? 2.96. Positive 2.96. Okay, so use the normal curve, estimate the percentage of women with heights below 66. So we're going to go to negative infinity is the lower limit. The upper limit is 0.654. 74%. Between 60 and 66 inches. So the lower limit is minus 1.65. Upper limit is 0.654. 69%. Above 72 inches. So 0.15%. Okay, note this is not 15%. The formula we're using, this original formula here, is already in percent. So the formula we've typed in, it's giving us the actual percent. In a law school class, the entering students averaged about 160 on the LSAT. The standard deviation was about 8. The histogram of LSAT scores followed the normal curve reasonably well. LSAT scores range from 120 to 180 among all test takers. The average is around 150, and the standard deviation is around 9. Okay, so what they're telling us here, this is in general how LSAT scores are distributed, but the question, if they were asking us a question about a general LSAT, what would you like a general LSAT? Like if we were going to some random class and we wanted to guess what percentage of the class would score below this, we would use these general statistics here. But they're asking us about this specific class here. What percentage of the class, this class? So this class averaged about 160. The standard deviation was about 8. So we're going to use that. We're going to assume a normal curve with this average and this standard deviation, because that's what the question is about. They're just giving us general LSAT statistics for, like, I guess, all over the country over a course of years. That this is what's averaged. If they were asking us about that, just in general, we're going to some random class, we're going to guess what the scores are going to be. We would use these statistics, but that's not what they're asking, okay? So about what percentage of the class scored below 166? What is 166 in standard units? Okay, how far is 166 from 160? It's plus 6. How many standard deviations is that? 6 divided by 8. 3/4. So what's the area on the normal curve from, this is standard units, from 3/4 and below? So 77%. One student was 0.5 standard deviations above average on the LSAT. About what percentage of the students had lower scores than he did? The area from, just do this. Like that. 69%. In figure 2, the percentage of women with heights between 61 inches and 66 inches is exactly equal to the area between 61 and 66 inches under the blank, and approximately equal to the area under the blank. Options: normal curve, histogram. Yeah, so this is what I've been talking about, trying to get you to understand the context of what we're doing. The percentage of women with heights between 61 inches and 66 inches is exactly equal to what? Here's figure 2. Between 61 and 66 inches, this area, the area under the literal histogram. Okay, so histogram. And approximately equal to the area under the normal curve. Approximately equal to the area under the normal curve here, which we could do it like, see? Okay, now let's move on to section 4, and this is going to be interesting. We're going to talk about what the textbook mentioned here, in that, what do you do if how do you handle a histogram that doesn't, you can't say it's normally distributed? So like the standard deviation and the average aren't good descriptive statistics in that case, so what do you do?